right, so we have this problem right here, a roller coaster. So notice the problem states that the Raptor, it's an outside loop roller coaster in which the riders are belted into seats resembling sky lift chairs. If the cars travel at an initial speed of 4 meters per second when they are at the top of the hill, determine the speed when they are at the top of the loop, and the reaction of the 70-kilogram passenger on his seat at this instance. Notice that we have that the mass of the car is 50 kilograms. The height of the loop, or from the first part, it's 12 meters, and the radius of the loop, it's 5 meters. They're asking us to neglect friction and the size of the car and passenger. So this is also pretty much also doing only conservative forces. So let's write some of the stuff that we have for this problem. So we know velocity 1, it's equals to 4 meters per second. We have the mass of the passenger to be 70 kilograms. We have the mass of the car to be 50 kilograms. We have the height, which is 12 meters, and the radius of curvature for the loop is 5 meters. All right, so we can label our points. So this will be point 1 right here at the top, and over here will be point 2 once the car is at this point. So notice there's not that much height difference. It does go down and goes to make the loops, but it should be able to do it clearly to clear the loop. All right, so we have to find what is the velocity at the top of the loop and what is the normal force exerted in this case. So let's, since we know also this is a smooth, right? So I think we gotta write down there's also a smooth, so no frictions, only conservative forces. So using conservation of energy, we'll have T1 plus V1 is equals to T2 plus V2. So that is the equation that we have right here for this problem. So if we start solving this problem, we can do first then the solving for V2. So doing this, we'll get 1/2 mass times V1 squared plus mass times gravity times the height at 1 equals to 1/2 mass times velocity 2 squared plus mass times gravity times the height at 2. Notice we do know all of these things. We know the V1, it's given in the problem. We know H1, we know H2, right? Because we know the radius. So if this is 5, then the total length here should be what? 10 meters, right? Because there's a total diameter of the circle. So we have height 2, and we're looking for V2. Notice we can also cancel all the masses, right? Because their masses are the same if we consider the whole system altogether, right? Both passenger and car. So doing that, and if we rearrange, we can get out of here, right? 1/2 V1 squared plus gravity times height 1 minus 1/2 V2, or not V2 squared, this is minus gravity times height 2, it's equals to 1/2 mass times, or not mass, 1/2 V2 squared. So if we multiply everything times 2, we'll get V1 squared plus 2 times gravity times the difference in between the height 1 and the height 2 equals to V2 squared. Of course, if we take the square root of all of that, right, and you solve, you should be able to figure out that V2, it's equals to 7.43 meters per second. So that is the velocity at point 2 right here when it's on the top of the loop. So with this information, now we have to figure out the normal force. So to do that, we can analyze this a little bit. So let's draw our free body diagram. So I'm going to draw it over here. So free body diagram. So we have our roller coaster like this, right? And notice that we have an outside loop roller coaster. So that means that the car goes on the outside of the loop, not on the inside of the loop. So if we can draw our little car, notice it will be, I mean, at this point it will be, upside down. We have maybe the top of the car, and this is one of those, I don't know if you've seen those, but it's the type of roller coaster, if you go maybe to like Six Flags, where you're hanging, right? This is your seat, and you're hanging from, the roller coaster, right? You're not, the rails are not below you, they are above you. So you're hanging, right, like this on chairs as you move forward. So this is like the kind of roller coaster that we have right here. So in this case, at this instance, if you go off the loop, your chair will be, kind of backwards. So I'm doing just, overall shapes right here. So this is, the back of your chair, and then we have, here the seats, and then we have the person, this is the person just sitting here, right? The block will representing the person. Anyways, that's their chair. It's on the outside loops, and that's the chair. So what forces do they experience? Well, we have that of course, there's a force of gravity. So mass times gravity. In this case, will be both the mass of the car and the object. Right? They both experience, we'd say mass of the person times gravity, and the mass of the car times gravity. Right? There's both weights right there. And we also see some normal force. Notice the normal force is, of course, in the direction of whatever's touching here. So in this case, the car is exerting a normal force. So I'm going to do here a normal force to the tracks. So there's a normal force right there acting downwards, because the direction in which it is touching, this thing. So that is the normal force for this one. That's how we do with this kind of roller coasters. So I guess we can simplify it over here. So just to show you a little bit more. I still have this one in my notes either way. So we have, for example, the seat, right? The seat right here, and the person. The person will be here by this block. So between the person and the chair, right, once again we said we're experiencing the mass of the person times gravity. And we see that the chair is also, once again here, is causing a normal force on the person. As the person is sitting, there's a normal force. So notice the way that this kind of roller coasters works is that the normal force helps you stay down on your seat. So if we once again draw just the person, what forces is the person experiencing? Well, it's the gravity or the weight of its own, person. So the mass of the person times gravity, and it's also experiencing the normal force caused by the seat of the, here. So, yeah, because we're looking at the reaction of the passenger on his seat at this instance. So yeah, we're not looking the specific whole track, but this kind of also happens in the situation. So yeah, if we just look at this specific scenario right here, the seat on the person, that's basically what I was drawing over here. So the way that these roller coasters work is that they are designed in such a way that when you go around the loop, with a certain velocity, you're actually your own weight and the seat itself, it's helping you stay down. If this normal force was not there, then what could have happened is that the person flies out, once they are out of the loop, right? Once they get out of the loop, they can of course just continue tangent to it and fly out of the thing. So the normal force is actually helping you stay down. So if we do here then summation of forces in the normal direction, right? We keep it in the normal tangential. So summation of forces in the normal direction, this is equals to mass times acceleration in the normal. So we have here then where we're going to say that down is of course positive because it's towards the inside of the curve. This is our tangent direction, right? This is our normal direction towards the inside of the curve. So we have normal force plus the mass of the person times gravity is equals to acceleration in the normal, which we know that is v squared divided by 2, and that will be v2, like that. So if you just rearrange out of here, so looking for normal force is equals to v2 squared over rho minus mass of the person times gravity. We know the velocity from before at state 2. We know the mass of the person. We know gravity. We know the radius of curvature, which is 5. All right, we know, once again, the radius of curvature. This is a round loop. So this radius of curvature, of course, we know as 5 meters. So when you substitute in the values, you end up getting that the normal force calculated is 86.2 newtons. So that is the normal force exerted from the chair to the person. So now the previous problem before this one, it's slightly different, where they're asking you to figure out what is the minimum initial velocity needed so the persons don't fly out of, once they are in the top of the loop. You guys can find that already in my notes. You guys can try it out. You just have to keep it in form of equation. But what will be try it out, use it as an exercise. In this same problem, let's say you do not know h or rho. Keep it as variables. What will be the minimum velocity required at point 1 so that the person is able to clear out the loop, just on its own under the influence of that initial velocity, right? What would it be? And right, so the passengers just make a loop without leaving contact with their seats. So in this case, we can assume that the normal force it's equals to 0, just about to do that. So you guys can calculate that. It's pretty straightforward. Try it out, and I think this will be the last video on this topic. The next video will already deal with the next lecture where it comes to the linear and angular momentum and impulse, as well as collisions. All right, that is it for this set of lectures. I'll see you guys tomorrow with the next videos. Until then, keep on study and good luck.